Hello everyone, and welcome to the Mathematecher channel again. In today's video, we have a number that we note as theta, which belong to the real open interval, 0 and pi over 2, and a sequence un that is defined in the set of the natural numbers by the recurring relation. Un plus 1 equals the square root of 2 plus un and a first term, u0, which equals 2 times cosine theta. We're asked at first to calculate the terms u1 and u2, and then to prove by a recurring reasoning that un equal 2 times cosine theta over 2 to the power of n. So, let's start by calculating the values of the terms u1 and u2. So according to the recurring relation that defines our sequence un, u1 would be equal to the square root of the sum 2 plus u0, which equals the square root of 2 plus 2 times cosine theta. That equals the square root of 2 times 1 plus cosine theta. Now, in order to get rid of the root and simplify this scripture, we will use one of the trigonometric identities about the cosine function that is known as power reduction formula. So this formula, which states that the square of a cosine of a real number theta over 2 equals 1 plus the cosine of theta, all over 2, allows us to replace 1 plus the cosine of theta by 2 times the square of cosine theta over 2. So we can write u1 as equal to the square root of 2 times the square of cosine theta over 2, which equals 2 times the absolute value of cosine theta over 2. Now, as it is shown in the unit circle that appears, since our real number theta is within the interval 0 and pi over 2, then theta over 2 would be within the interval 0 and pi over 4. So the cosine of the angle that measures theta over 2 radius is strictly positive, which means that the absolute value of cosine theta over 2 equals cosine theta over 2. Therefore, the term u1 equals 2 times cosine theta over 2. As for the term u2, according to the recurring relation, it would be equal to the square root of 2 plus u1, which equals the square root of 2 plus 2 times cosine theta over 2. That equals the square root of 2 times 1 plus cosine theta over 2. So once again, in order to simplify our scripture, we use again our power-reducing formula to replace 1 plus cosine theta over 2 by 2 times the square of cosine theta over 4. So u2 would be equal to the square root of 4 times the square of cosine theta over 4, which equals 2 times the absolute value of cosine theta over 4. And again, as it is shown in the unit circle in the figure, since the number theta over 2 is within the interval 0 and pi over 4, then theta over 4 would be within the interval 0 and pi over 8. So the cosine of the angle that measures theta over 4 radius is strictly positive, which means that the absolute value of cosine theta over 4 equals cosine theta over 4. Therefore, the term u2 equals 2 times cosine theta over 4. Now let's prove that the general term un equals in terms of n 2 times cosine theta over 2 to the power of n. So, as we will be proving this by induction, we will at first verify that the first term u0 equals indeed 2 times cosine theta, according to this scripture. And then we will prove that un plus 1 equals 2 times cosine theta over 2 to the power of n plus 1, assuming that for a random value of the natural number n, un equals 2 times cosine theta over 2 to the power of n. So, for n equals 0, we have u0 that equals 2 times cosine theta, which can be written as equal to 2 times cosine theta over 2 to the power of 0. Which means that for the first value of n, which is 0, our general term formula in terms of n is true. We'll note this as assertion number 1. Now, if we suppose that un equals 2 times cosine theta over 2 to the power of n for a random value of n, the term un plus 1, that equals according to the recurring relation that defines the sequence un, the square root of 2 plus un, would be equal to the square root of 2 plus 2 times cosine theta over 2 to the power of n, which equals the square root of 2 times 1 plus cosine theta over 2 to the power of n. And by using our power-reducing formula about the cosine function, again, we can replace 1 plus cosine theta over 2 to the power of n by 2 times the square of cosine theta over 2 to the power of n plus 1. So un plus 1 would be equal to the square root of 4 times the square of cosine theta over 2 to the power of n plus 1, which equals 2 times the absolute value of cosine theta over 2 to the power of n plus 1. Now, since the number theta over 2 to the power of n plus 1 is within the interval 0 and pi over 2, then the cosine of theta over 2 to the power of n plus 1 is strictly positive, so its absolute value equals cosine theta over 2 to the power of n plus 1. So the term un plus 1 equals 2 times cosine theta over 2 to the power of n plus 1. Therefore, we've proved that if the term un can be written as equal to 2 times cosine theta over 2 to the power of n, then the term un plus 1 can be written as equal to 2 times cosine theta over 2 to the power of n plus 1. We'll note this as assertion number 2. Now, as the assertions 1 and 2 represent the 2 steps of the induction proof that we've accomplished, we can deduce that the general term un equals 2 times cosine theta over 2 to the power of n, whatever the value of the natural number n is. After that, as always, thank you for watching. Subscribe to the channel, like and share the video. And until the next one, we wish you the best.